Today we are going to continue on solving problems on the kinetics of rigid bodies. And I want to mention a point here that all these examples that we are solving, they are not just random examples, random questions. They're kind of like cherry-picked examples that each of these examples represent a category of problems that we see in problems in dynamic textbooks, and each of them have a kind of like a point, a trick to kind of like to be able to solve them. For example, this problem that we have here, we will see that kind of like connects the kinetics of rigid bodies with kinematics in curvilinear coordinate systems. And this is a kind of like a category of problem that if you are able to solve basically one of them, you will be able to deal with other problems that are kind of like in the same category. So in a way, part of the material in the course is kind of like contained in these examples that we are solving. I think that the best way to kind of like teach these points is just kind of like by solving examples. Otherwise, we would just say that all the dynamics is just to draw the free body diagram and write down the Newton's equation. But that's not what we wanted to do, especially in this course that is intermediate dynamics. We want to kind of like learn about all these tricks, all these kind of like subtle details that we have in dynamics problem. So that's one point that I wanted to mention, and that's why I actually I emphasize on kind of like going through these examples. It's not that this is just an example and you don't need to solve it again. By kind of like going through them again by yourself, writing down the equations and try to solve them again, you kind of like learn the point of that example, or kind of like it's like you are going through the lecture. So the point of the lecture is kind of like contained in these examples. So with that being said, let's solve this example. So the question is that find the forces at the front and rear wheels find the forces at the front and rear wheels at the moment the skateboard enters the curved path. Friction is negligible. So we have a skateboard here. It's just going with the constant velocity of v0 to the right. It has a mass of m, length of l, and at this point here we have a kind of like a quarter of a circle. We have the radius of curvature for this circle, and we are asked to find the forces at the front and rear wheels as the skateboard enters the curved path. So right at this moment that the front wheel is at this point, at the beginning of curved path, we want to see what are the forces on the wheels. So let's solve this. So before considering the skateboard at the kind of like a beginning of curved path, let's see what are the forces at the wheels on the straight line. So we have a skateboard here, and so let's say that this is on the straight line. So let's have the wheels here, for example. So that's one wheel, the other wheel here, and we have the force of gravity acting on this skateboard. So here is just the force of gravity. Let's show this with mg. We have the force at the front wheel, which, because we don't have any friction, it's gonna be normal to the surface, normal to this straight line. So we are going to have, let's say here, this is F, force at front wheel, so F of F, and here we have this force, which is force at the rear wheel, or FR. So these are the forces that are acting on the skateboard on the straight line. So if we write down the Newton's equation, because basically the skateboard is just moving with the constant velocity to the right. There is no acceleration, so we expect kind of like equilibrium. So I can say that sigma f is equal to mag, and by the way, here is just a g center of mass. And basically here ag is equal to 0, ag, this is equal to 0, and therefore sum of all the forces that are acting on the skateboard is 0. So from here we get sigma Fy is equal, so forces in the x direction and also forces in the y direction. We don't have any forces in the x direction, so we are going to have all the forces, sum of all the forces in the y direction to be equal to 0. So this is equal to 0, and here we get f of f plus f of r is equal to mg. So that's one equation. The second equation that we can write down here is just the Euler equation. So I can say that sigma mg is equal to ig alpha. And again, because this skateboard is just moving to the right without any acceleration and any rotation, alpha here is 0. So we said that we don't use the vector notation here because we are in 2D, everything for the Euler equation is in the k direction, normal to the plane. So here the alpha is equal to 0, so this is equal to 0, therefore this is 0, and now we can sum up all the moments due to these forces. So around this point G we get f of f basically times L over 2, because the length of the skateboard is L. So this is in the positive direction, and then minus f of r times L over 2 equal to 0. So from here we get f of f is equal to f of r, and if we substitute this into this equation, we get f of f is equal to f of r is equal to mg over 2, which makes sense. Because of the symmetry that we have and because there is no acceleration, half of the weight of the skateboard is carried by the wheel at the front, and half of the weight is going to be carried by the wheel at the end, at the rear side. So that's when the skateboard is on the straight line. Now let's imagine the skateboard at the moment that enters the curve path. So let me copy this. This is actually a good example to kind of like check for your intuition to see what happens when the skateboard enters the curve path. What happens specifically to the forces at the front and rear wheels. Do they increase? Do they decrease? Does one of them increase, one of them decrease, or what happens if you can kind of like, if you think about it, that's a good test for your intuition to see. For example, there are 4 scenarios here. One is just both of these forces increase. Second one is that both of them decrease. The third scenario is that the force at the front wheel increases, this force decreases, and by increase and decrease I mean from this equilibrium compared to this equilibrium position that they were mg over 2. So the third scenario is that this force would be larger than mg over 2 and this would be smaller than this, and the last scenario is that this one would be smaller than this and this one would be larger than this. So that's the kind of like, you can pause the video and think about it to see what your intuition says about this problem. So let's kind of like erase these dimensions here. We want to have the wheel exactly at the beginning of the curve path. So let me actually copy this. Oops. think this is harder than I thought, but let's give it a try. So let's just cut it actually. So here, and then, okay, that's not bad. So this is at the moment that the front wheel enters the curved path. So here the velocity again is, at that moment, is just v0 to the right. Oops. Let's move this over. It's not working. Doesn't let me to cut this piece and bring it to the right, but that's okay. So just let's leave it there. Let's actually erase it. We know that the velocity is just v0. Now my pen is not working. Oh, I see what's going on. So sorry for that. I think it got messed up when I copied that figure over there. Okay, there we go. So that's the velocity here at this moment, exactly where the skateboard enters the curved path. So this is v0. Okay, so now let's show the free body diagram here. So we are going to have again mg, force of gravity here. So this is mg. We're going to have this force, f of f, and also this force, f of r. So this is mg, this is f of f, and this is f of r. So let's start again with writing down the equations, the Newton's equation. So sigma f is equal to m a g. And here again we have 0 in the I direction, x direction. So let's also show a coordinate system here. So let's say this is, let's use a blue color. So this is x direction, and this is y direction. So x and y. So I can say here that we don't have any forces in the x direction, at least at the beginning. Once the wheel is on the curved path here, not at the beginning, but over here in the middle, we are going to have the normal, the surface force in the normal direction to this curved path, and that force will have both vertical and also horizontal components. But once we are at here, the force, the reaction of the surface is going to be normal to this path, and here the normal is just in the vertical direction. So we don't have any forces in the x direction, so 0 in the I, plus we're going to have f of f plus f of r minus mg in the j direction. This is equal to m a g x in the I direction plus a g y in the j direction. Okay, so here we get a g x is equal to 0, and also f of f plus f of r minus mg is equal to m a g y. So that's the Newton equation. Let's go to Euler equation now. So sigma m, again around point G, which is always the safest option to write down because we know that this is always true, the short version of Euler equation. So let's calculate the moments here. So we are going to have f of f times L over 2, and the moment is going to be in the positive k direction. Or you can do the vector calculation. You can say that this is the moment of this force would be r cross f, and r here is just L over 2 in the I direction cross f of f in the j direction, and the result would be f of f times L over 2 in the k direction. So, but you can also use the right hand rule to figure out the direction of the moment. So f of f, L over 2, and similarly here the moment of this force would be negative in the minus k direction. So we are going to have minus f of r L over 2 is equal to Ig. So we said that for kind of like a long rectangle here, that we have only the length of it and the other dimension is very small compared to the length. The moment of inertia for this shape of a structure around its center of mass here at the G. So here this point is G. So this is basically G. The moment of inertia is 1 over 12 m L squared alpha. So this is I of G, and that's alpha. Okay, so here if we simplify this equation, we get f of f minus f of r is equal to, so we can multiply both sides of this equation by 2 over L, and we get m L over 6 alpha. So let's highlight this equation. So this is actually the second equation that we have. The first equation that we had over here is this equation. Remember that we are after f of f and f of r. So here, this is the first equation and second equation. And from the Newton's equation in the x direction, we got basically just acceleration in the x direction equal to 0. So nothing important for us in that equation. So here we have two equations. So far, two equations. And let's count the number of unknowns here. So we have f of f, f of r, a gy, and also alpha. So we have two equations, 4 unknowns here. And we have to figure out other equations to be able to solve this problem. So let's see what can we get from this problem on the kinematic side. On the kinematic side, this curved path here, because we have the radius of a curvature and because we have the velocity of this skateboard at this moment, we can actually figure out the acceleration of this point. So let's call this point A, and let's call this point B. And the middle point is just G, the center of mass. So here I'm saying that we should be able to figure out the acceleration of this point A. So this is a rigid body, and we can calculate the velocity of this point on the rigid body. So nothing is wrong with that. So let's calculate A of A. So A of A would be, and we want to write the acceleration of point A based on point G, and also based on the kind of like geometry of the path. So let's calculate the acceleration based on the geometry of the path. So the velocity of this point, I can say that I can write down the velocity of this point at any coordinate system that I want. But here, one particular coordinate system that I like to use here is just curvilinear coordinate system. If I write down the acceleration of this point in the curvilinear coordinate system, it is going to have a tangential direction, a t in the t direction, plus a of n in the n direction. So this is from kinematics that we had. We are in 2D, we can write down the acceleration in this format. And at that moment, t is actually the unit vector t is equal to I and n is equal to j. So here at this moment, t is going to be tangent to the path, which is going to be in the x direction, and n is going to be normal to the path. So it's going to be in the j direction. So I can say that at that moment, t is equal to I and n is equal to j at the beginning. Once the skateboard is in the middle of the curve path, you can see that the t would be again in the tangent direction, so it's going to have an angle with the x or y direction, and also n is going to have an angle with the x and y direction. So these equations that we wrote down here is just true at the beginning. So if that's true, I can say that a of a is equal to a of t in the I direction plus a of n in the j direction. So this is the tangential acceleration and this is the normal acceleration. And we said that the normal acceleration in the curvilinear coordinate system, we had an expression for that. We said that this is equal to v squared over r. So let's see if we have these quantities. We do have these quantities. V of velocity of this point at this moment is just equal to v naught. The skateboard is about to just enter this path, so its velocity was equal to v naught before this point, and it is equal to v naught again at this point. So we have the velocity of point A at this moment, and we also have the radius of curvature. So we said that this is a quarter of a circle, and the radius of curvature here is just r. So we can say that an is for our problem is going to be v naught squared over r, or this was actually rho. So let's write down this in the general format. For the curvilinear coordinate system, we had this equation, and here we have rho, the radius of curvature, and also we have the velocity. So therefore the acceleration of point A would be a of a would be a of t, which we don't know what this is, the tangential acceleration, plus v naught squared over r, which we do have this quantity. So this is going to be in the j direction. Okay, so that's one relationship, one equation for acceleration of point A. Also, let's write down the acceleration of point G based on point A, because here remember one of our unknowns was AGY, the acceleration of center of mass in the y direction. Let's see if we write the acceleration of G based on A, if we can find AGY. So I can say that for a rigid body, so AG is equal to AA plus omega cross r plus alpha cross r g with respect to A. So here we had AA, so I can say that AG, this is equal to AT in the I direction plus V naught squared R in the J direction. And this term is equal to 0 because the skateboard is about to start rotating. So its angular velocity is 0, but its angular acceleration is not 0. So this is just a moment, kind of like we said that when we say something is just starts to moving, its initial velocity is equal to 0. Or when we say that this starts to rotate at this point, so its initial angular velocity is going to be 0. So the angular velocity at this point for the rigid body is equal to 0, but the angular acceleration is not. So here we can say that the initial angular velocity is equal to 0. So therefore this term is equal to 0. So then we have plus alpha. Let's say alpha is unknown in the k direction, cross rg with respect to a, which would be minus L over 2 in the I direction. So we are going to have AT in the I direction plus V naught squared over R, and here K cross I would be J, so we are going to have minus alpha L over 2 in the J direction. That's the acceleration of center of mass. So this is good. This equation is good because now we can say that we have an expression, another equation for AG and alpha. So remember AG and alpha, they were both among our unknowns. So now we have another extra constraint here basically. So another extra equation here. So I can say that AGX is equal to AT, this was equal to 0, therefore AT is equal to 0. There is no tangential acceleration at the beginning of the curve path. And also I can say that AGY is equal to, this is G, so AGY, this is equal to V naught squared over R minus alpha L over 2. So let me highlight this equation. This is another equation that we have that gives a relationship between AGY and also alpha. V naught, R, and also L, they are all known. They are given in the problem. So still we have 4 unknowns and 3 equations. So let's see if we can find another equation, another constraint that gives us another equation so that we would be able to have 4 equations and 4 unknowns. So we wrote down the velocity of the acceleration of A. We wrote down the acceleration of G based on A. I would say let's also write down the acceleration of B based on A. So, and we are going to have one extra geometrical constraint over there. So I would say AB, I can write down the same way. AB is equal to AA plus omega cross R plus alpha cross R B with respect to A. So again, this term is equal to 0 because omega is equal to 0, and we have AB is equal to AA, which is, where is the equation for AA? AT in the I direction, which we said that AT is equal to 0, so this would be only V naught squared over R in the J direction. So we are going to have 0 in the I direction. Let's write that down. V naught squared over R in the J direction. And this term would be plus alpha K cross RB with respect to A. So that would be minus L in the I direction. So we have V naught squared over R minus alpha L in the J direction. So here is the constraint, the extra constraint that we were looking for. I would say that the acceleration of point B at the beginning here is just in the y direction would be equal to 0. So after this skateboard enters this curve path, the point B would be still on the horizontal line on this surface. So the point B wouldn't move in the y direction, and because it is not moving in the y direction, its acceleration in the y direction will also be 0. So we can say that ABY which is all we have for AB. Actually, we can say that AB, if I had said that AB is equal to 0, that would be kind of like surprising and hard to tell, but it's just, I would say here that after writing down AB, I would say that ABY is equal to 0, or AB is basically, if this is 0, AB is equal to 0. But we can all understand this, that ABY is equal to 0. When point A goes to the curved path, point B is still on the horizontal line, and it is not moving in the vertical direction. So this is equal to 0. So this is constrained. These are kind of like points that you learn by solving these problems. So if this is equal to 0, this term is equal to 0. V naught squared over R minus alpha L is equal to 0. And look at this equation. We can extract alpha here. So we can say alpha is equal to V naught squared over R. So let's highlight this equation with a yellow box, because we just figured out alpha. We weren't asked to find alpha, but that's good that we found alpha, and it helps us to find the forces at the wheel. So now let's kind of like bring these equations down, and kind of like we have 4 equations right now, and we should be able to find the 4 unknowns that we have. This is the first equation we have. This is the second equation. This is the third equation. This is the third equation, and the fourth equation is just an alpha, which is nice because we can find alpha. So here I can say that AGY, let's find also AGY here, and then substitute AGY into this equation. And also we have alpha, so we get 2 equations on f of f and f of r. So we want to see what happens on the force on the wheel, to see if they increase or decrease. So let's go here, AGY. AGY is equal to V naught squared over R minus alpha, which is, we dropped the L here. So this is V naught squared over RL. So here AGY would be V naught squared over R minus L over 2 V naught squared over RL. And this gives us AGY is equal to, so we can cancel out L with each other. Here we have V naught squared over R minus 1 over 2 V naught squared over R. So this is V squared over 2R. So that's AGY. And now let's substitute these equations, these 2 quantities, into the first 2 equations that we had. So the first equation we had was the Newton's equation in the y direction. So it was f of f plus f of r minus mg is equal to m AGY. So that would be m v naught squared over 2r. The second equation that we had was f of f minus f of r is equal to, I think, 1 over 6 ml alpha. Let's see if that's correct. So yeah, ml over 6 times alpha, and we have the value for alpha. So alpha is equal to v naught squared over rl, which this gives us L. We can cancel out the L's here. We have m v naught squared over 6r. So now we have 2 equations on 2 unknowns, f of f and f of r. I can just sum up the left hand side of these equations with each other and also right hand side with each other to find out the value of f of f. So I can say that here. So if I sum up these equations with each other, here f of r will cancel out with minus f of r, so we get 2 f of f minus mg. We had a minus mg over there. And here this would be m v naught squared over r 1 over 2 plus 1 over 6. So 1 over 2 plus 1 over 6. Which we can write down this 3 over 6. This would be 4 over 6. And that would be 2 over 3. So 2m v naught squared over 3r. So f of f would be half of this quantity if we divide both sides of this equation by 2. And we have to also bring the mg on the right hand side. So f of f would be, so I bring mg over here and then divide both sides of the equation by 2. So this would be mg over 2 plus this quantity over 2. So this would be m v naught over 2 over 3r. So the force at the front wheel increases with as the skateboard enters the curve path. And what is that? The value of the that increase just mv squared over 3r. Let's see what happens to the force at the rear wheel. So I can just substitute this equation into this equation or into this equation and find out f of r. So f of r, I can bring f of r to the right hand side and bring this to the left hand side. So f of r is equal to f of f minus m v naught squared over 6r. And this is mg over 2 plus m v naught over v naught squared over 3r. This is for f of f minus m v naught squared over 6r. So here we get fr is equal to mg over 2, and here we have 1 over 3 or 2 over 6 minus 1 over 6, that's 1 over 6. So plus m v naught squared over 6r. So the force at the rear wheel also increases by this much, m v naught squared over 6r. So before entering the curve path, the force at both wheels was mg over 2, and after entering the curve path, the force at both wheels actually got increased. And the value of increase here is just for it increases more for the front wheel compared to the rear wheel. So this is for this example. As I said, this is kind of like an example that combines the kinetics of rigid bodies with kinematics of particles. Here, when we were writing down the acceleration of A in the curvilinear coordinate system, we were saying that this is a point, this is basically a particle. So this problem, this example kind of like combines the kinetics of rigid bodies with kinematics of particles in curvilinear coordinate system. And it's a kind of like example that we see also in everyday life, whenever you kind of like, let's say this is a car that is just entering this path, the force at the wheels actually get increased. So this is for this example, and I will write down the next example so that we can go through it. This is the second example that we want to solve here. So we have a rod here that is hanging with these two strings here that are pinned at point O, and we have a scissor here that we want to cut this string here, and exactly at that moment that we cut this string, when that string is gone, we want to see what happens, what is the tension in the other string here. So what is the T right after cutting the string here? So we cut this string here, so let's call this point A, for example, and this is this point B. We cut this string, we want to find the tension in this string. the length of this rod is 4 meter, its mass is 3 kilogram, and we have the gravity in this direction, downward direction. So again, let's start by drawing the free body diagram and then writing the Newtons and also Euler equation for rigid bodies. So for the free body diagram here, if I have, let's say this is the rod, and when we cut that string, so there is no force over there, so we're gonna have only two forces here. One is just this force of gravity, and the other one is the force of this string, the tension in that string. So here we have T, and this angle is 60 degrees. So this is 60 degrees, and this is mg. And the center of mass here is just G, so at the center. So let's write down the Newtons here. So here, Newton's equation, sigma F is equal to ma g. We have T cosine. So this is the, let me also draw the coordinate system here. So let's say this is the x-axis, and this is the y-axis. So x and y. So in the x direction, I direction, we have T cosine 60 in the I direction, and in the j direction we have plus T sine 60 sine 60 minus mg here. This is equal to m a g x I plus a g y j. So from this equation we get two equations, two scalar equation. So here T cosine 60 is equal to m a g x, and we also have T sine 60 minus mg is equal to m a g y. So that's for Newton, and now let's write down the Euler equation. So again, I write down the version of Euler equation that calculates the moments around the center of mass, because that makes the equation easier. So Ig alpha sigma m is equal to Ig alpha. Here, around the center of mass, so the moment of the gravity force would be equal to 0 because it is passing through that point, and we only need to calculate the moment of this. And here I do it with a vector notation so that you can see how we can write that down. So here I would say that the moment of this force, the T force, the string force, is just R. So let me draw R here. So let's use a yellow color here. So this is R. When we say that we calculate the moment around point G, that is what we mean. So we have a vector here, should be horizontal, but you get the idea. So here R, that's a kind of like that's a vector that connects our reference point to one point on the line of action for the force that we are trying to calculate this moment. So here I would say that R cross T would be I G alpha, and we know that this is always in the k direction for 2D kinetics problem. So this is the vector notation. So let's calculate this. R here is just minus L over 2 in the I direction. So if we look at this picture here, R is basically half of the length of this rod here, and the length of the rod is L, so this would be L over 2 in the minus I direction cross T, and T would be T cosine 60 in the I direction and T sine 60 in the J direction. So we want to calculate the moment of that force. So this is cross t cosine 60 in the I direction plus t sine 60 in the j direction. And this is equal to Ig. And we know for a rod, this is 1 over 12. So 1 over 12 m L squared alpha k. So here I cross I is 0 and I cross j is k. So we get T L over 2 minus sine 60 in the k direction, because I cross j is k. This is equal to 1 over 12 m L squared alpha in the k direction. So from this equation we get, so let's multiply both sides by 2, we get minus T L sine 60, or let's substitute sine 60. So sine 60 is the square root of 3 over 2 is equal to 1 over 6, and I can also multiply by 2 so that we can have TL square root of 3. So I should multiply this by 4. So I get 1 over 3 m L squared alpha. I can also cancel out one of the L here. So here we get minus t square root of 3 is equal to m L alpha over 3. So these are the equations that we have so far. So this is one equation. Let's see if I got this right. So this is ml alpha. Yeah, that's right. So that's one equation. The other equation here is this equation. This is the second equation that we have. And this is the third equation. Or let's do this actually. So these are two equations. And we have one equation over there. So 3 equations in total. 3 equations. And what are the unknowns here? So we have t, we have agx, agy, these are the unknowns, and also alpha. So t, agx, agy, and also alpha. So again, we have more unknowns than equations we have. So we need one more equation so that we can have 4 equations, 4 unknowns. So how can we get the other equation? So I would say let's write down the velocity, the acceleration of point A based on point O, because basically this string is kind of like stretched, and we can consider stretched strings or cables in dynamics as rigid bodies. So we kind of like ignore their deformation when they are under stretch. Basically all of the rigid bodies, that's why we call them rigid bodies. There is no deformation in the objects that we have considered so far. And here for the string, we can also say that if it is under stretched for a string and a cable, and if we ignore their kind of like their deformation, or here the elongation of the string due to this force, they are basically rigid bodies. But strings and also cables under compression, we can't say that they are rigid bodies because they can't bear compressive force. But for tension force, they can bear that. So for a string here, I can say that I can write down the acceleration of A based on O, considering that that's a rigid body. So I can say that AA, okay, so AA is equal to, so again I'm trying to just use kinematics to come up with another equation so that I can solve the problem. This is, as you can see, this is the theme in these kind of problems. Writing down the Euler and Newton's equation, and then using the constraint, the geometrical constraint, the constraint from kinematics, to come up with more equations so that we can have the same number of equations as the same number of unknowns. This is a very important analysis here in solving problems, and basically it just tells you that what direction you have to go. If we had the same number of unknowns as same number of equations as unknowns, then we just go ahead and solve them. But once we are at here, it is clear that we need more equation to be able to solve for the unknowns. So let's write down the acceleration of A based on point O. So I can say A of A is AO plus omega cross R. And here this is A with respect to O plus alpha cross R A with respect to O. This is A. So here, for point O, because it is a pinpoint, its acceleration is equal to 0. So that term is equal to 0. And also here, because again we want to see what happens right after we cut the string, the initial velocity and also initial accelerations in the problem here would be equal to 0. So as we cut this string, this rod starts to rotate, and therefore this string is going to rotate, but at that moment its initial angular velocity is equal to 0, but angular acceleration is not equal to 0. So we can say that my pen is acting up again, so this term is equal to 0. So we have A of A is equal to alpha cross R A with respect to O. And actually we can calculate this, or we can get our constraint just by analyzing this. So what do I want to get from this equation? So this equation tells me that the acceleration of point A should be normal to RAO. So the takeaway from this equation is AA is normal to RA with respect to O. So now let's write down the acceleration of point A based on point G. So we wrote down the acceleration of this point based on this point, and now let's just write down A based on point G, center of mass, to see if we can come up with an equation. So A of A is equal to AG plus omega cross R. That point A is basically kind of like common between the string and also the rod. So that's why we are writing down the acceleration of this point one time based on O and one time based on G for the rod. So this is AA is equal to AG plus omega cross R plus alpha cross R A with respect to G. And this is equal to, again, this term is equal to 0 because omega is equal to 0 at the beginning for the rod. So we have AG, we have AA is equal to AG plus alpha, so it's unknown, we consider it as alpha in the K direction, cross R A with respect to G. So that would be minus L over 2 in the I direction, or L over 2 in the minus I direction. So here we get, let's also decompose that vector, AGXI plus AGYJ. And here we have K cross I, that's J, so we have minus alpha L over 2 in the, again, J direction. So therefore AA is equal to A gx plus agy minus alpha L over 2. This is in the I direction and this is in the J direction. Okay, so we said that AA should be normal to RAO. So let's highlight this equation here. This is the constraint that we got for the acceleration of point A. And here we have this equation for point A. So I would say that this vector, acceleration of A, should be normal to RA with respect to O. And RA with respect to O, we know that this is basically in this direction, in the direction that makes the angle of 60 degree with the horizontal direction. Or if you want to say in this direction, RA with respect to O, you want to say that this is going to be in this direction. Doesn't matter, because the acceleration is normal to this line, so it is normal to AO as well as normal to OA, because the acceleration is normal to a line, so it doesn't matter if it is AO or OA. So I would use the unit vector along this line to represent this line and say that the acceleration of point A should be normal to this line, and the unit vector across along this line would be just cosine 60 in the I direction, sine 60 in the J direction. That represents this line. So I would say AA, so we want to apply our constraint AA dot, let's say AO should be, AO unit vector should be equal to 0. Again, doesn't matter, when we say it is normal to A with respect to O, we can say that it is also normal to RO with respect to A. So here we have this vector. We can say that this is the dot product. We can say that A, G, X in the, or let me write it down here actually. So this would be A, Gx times cosine, or let's write it this way, Agx in the I direction plus Gy minus alpha L over 2 in the J direction, and the whole thing dot AO, which is cosine 60 in the I direction plus sine 60 in the J direction. Okay, so let's do this dot product. So we get Agx cosine 60, which is 1 over 2 times 1 over 2 plus Agy minus alpha L over 2. So this is 1 over 2. Alpha L over 2 times sine 60, which is a square root of 3 over 2, should be equal to 0. So we can cancel out the 2's here. We can multiply both sides of this equation by 2, and basically we get Agx. So Agx is equal to minus square root of 3 Agy plus the square root of 3 alpha L over 2. So when we bring these terms to the right hand side, this term would be minus, we have to multiply by square root of 3, and this term would be positive, we have to multiply by square root of 3, and we have alpha L over 2. So that's our fourth equation that we were looking for. So let me highlight this equation. Okay, so now we have 4 equations, 4 unknowns, and we should be able to solve for T, alpha, Agx, and Agy. Here we are after just T, but we can solve for all of these unknowns. So let's see how we can do that. So here we have t cosine 60 is equal to m, and we have the numerical values of these parameters. So let's substitute them in. So t cosine, let me copy this equation here. Let me bring this down. Okay, and we had, I think, m4 kilogram or m3 kilogram, L4 meter. So let's substitute that. We get from these equations, we have t cosine 60, which is t over 2 is equal to 3 times agx, or I can multiply both sides by 2 and I get t is equal to t is equal to 6agx. This equation gives me t is square root of 3 over 2, t is square root of 3 over 2 minus mg, this is 30, is equal to 3agy. Let's write down the other two equations that we have. So one is here, minus t is square root of 3 is ml alpha over 3, so minus t square root of 3 is equal to ml alpha, or ml is 12, so let's do the multiplication here. So let's check this. Yeah, minus t square root of 3, this is m is 3, it cancels out with this 3, we have L alpha, and L is 4 meters, so that's 4 alpha. So here we have 4 alpha. And the last equation here we have agx. I'm just rewriting that equation. It's equal to minus 3 agy plus square root of 3 alpha L over 2. So let's see how we can find t. So if I substitute, we can find ag or agy based on t, and then I can substitute that here. We get agx based on t and alpha, and I can substitute that over there, and we get one equation based on t and alpha. We have another equation based on t and alpha, and therefore we should be able to find t. So here I can substitute, I lost my way here, so I can substitute here for agx based on let's find agy based on t. So here agy is equal to, divide both sides of this equation by 3, so we get t square root of 3 over 6 minus 10. That's agy. And now so this is from this equation. And now let's substitute this equation into this equation. We get agx is equal to minus square root of 3 times agy, which is t square root of 3 over 6 minus 10 plus square root of 3 alpha L over 2. Okay, so here we get agx, just simplifying this, we get, this is going to be 3 over 6, that's going to be minus t over 2 plus 10 square root of 3. And here we get plus square root of 3 alpha L over 2. And now let's substitute this equation for agx into this equation. So here, substitute this equation into this equation. So t is basically 6 alpha gx. So t is equal to 6 times this term. So that would be minus 3t plus 60 square root of 3 plus 3 square root of 3 alpha L. That's the first equation. The second equation here is that minus t square root of 3 is equal to 4 alpha. So minus t square root of 3 is equal to 4 alpha. And basically here we get, so here we have 40 minus L is also 4 meters, so I can also substitute for L. L is 4 meters. Yeah. Go up here. L is 4 meters. So I can say here this would be 12 square root of 3 alpha. So 12 square root of 3 alpha is equal to, so I'm bringing this term and this term to the left hand side and leave this term here. So this would be 60 square root of 3. And here we have basically, let's actually do this. Let's write down alpha based on t and then substitute into that equation to find for t. So alpha is minus t square root of 3 over 4. And now we substitute this equation into this equation. So, oops. So here we get 40 minus 12 square root of 3 times alpha, and alpha is minus t square root of 3 over 4 is equal to 60 square root of 3. And here we get, so this is 40 again. Here we have 3 times square root of 3 times the square root of 3, that's 3 times 12, that's 36. 36 over 4, that's 9. So we have plus 9t is equal to 60 square root of 3. And here's the t that we were looking for. So this would be 60 square root of 3 over 30. So hopefully we didn't make a mistake in this calculation, but basically you get the idea. The key here was that to write down the acceleration of point A, let me go up here, the acceleration of point A based on point O, and also acceleration of point A based on point G, based on the equations that we had to relate the acceleration of 2 points on rigid bodies. Here we argued that this string, when it is under stretched, it can be treated as a rigid body, and we don't have any kind of like, the only deformation that we have in this course is when we have springs. Other than that, we don't have any deformation in rigid in the bodies that we have. That's why we call them rigid bodies. And also here, because the only point is that to mention that this string is under tension, and therefore it can be treated as a rigid body. And that enabled us to basically use the equations for the rigid bodies to write down the acceleration of A based on O. We can also write down the acceleration of A based on G, and then we said that from the first equation we got that the acceleration of A should be normal to this line, and we could apply that on the second equation when we were writing the acceleration of A based on G to get a constraint on the acceleration of the center of mass and also alpha, and that gave us the fourth equation to solve this problem. And here we were looking for t, but basically after we can solve all the 4 equations to get all the unknowns. And again, here you can make the comparison to just, I leave this up to you guys to calculate to see how this force, how the force in the string increases before and after cutting the string. So you can consider that, for example, this is also 60 degree, and calculate the force in the string before we cut this, and then we have the force after we cut this string, and you can make the comparison to see how that force, how much that force increases. So that's for this problem. And I want to also add a point regarding one of the questions that we solved, I think, last lecture. So remember that we had a kind of like a truck, and we had a cylinder that it was rolling on the truck. So let's say this was our kind of like the schematic for the truck that we had. And we had, oops, this one is much larger. Okay, so let's say this is our truck, and we had a cylinder here, and the problem was that this truck starts is moving to the right with a constant acceleration of a, and we said that how much does it take for this disk here to, this distance was d, this radius was r, and we said that assuming that we have pure rolling, how long does it take for this disk to fall off the truck? And we solved this. The point that I want to mention here is that, so here we said that, you know, we have pure rolling, and I want to see if we are given this problem in general, how to figure out if we have pure rolling or not. And the key here is that when we were solving this problem, we considered kind of like f of f, the force of friction. So it was in this direction. Oops. Oops. Again, my pen is not working. Okay, so let's just try it here. So we had force of friction in this direction, and we treat it as an unknown, and we found this expression. We found the value for the friction force, or we could find it. You know, it was one of our unknowns, and we had same number of equations as same number of unknowns, and we could solve for all of the unknowns. And the key to kind of like see if we have pure rolling or not is that to calculate this f of f, we treated this as an unknown. We got an expression for this, or we could get an expression for this, and I don't remember if we solved for the final value of this, but basically we were able to find f of f. And the key here is that if the value that we find for f of f, if it is larger than mu s n, and here n was just mg, so because we didn't have any, this is mg and this was n. So because we didn't have any motion in the vertical direction for the disk, we had n equal to mg. So if this force was larger than mu s n, remember this is the maximum maximum friction force for a stationary friction. And if the value of the friction force is larger than this, that means that we don't have pure rolling, and the disk is actually slipping while rotating on this surface. So this is a key kind of like parameter. This is how we figure out if we have pure rolling or not. We assume that we have pure rolling, we solve the problem, we find the value for f of f. If that value is smaller than this, then we are okay. We say that, okay, we have the friction force has not reached its maximum, which is mu s n, if it is smaller. So if f of f is smaller than mu s n, okay, that's okay. That means that we have pure rolling. But if it is not, so pure rolling. But if that's not the case, if we have f of f larger than mu s time n, then we don't have pure rolling anymore, and we have slipping here. So the disk will also slip at the same time that it is rotating in this direction. So when we were writing down the kinematic equations here, we should add the acceleration for sliding also for this point in the horizontal direction. So that would add one unknown to our problem, to the set of unknowns that we had. So we had the acceleration for this point A slid, that is unknown. We don't know how much sliding we have. So you might say that that adds one more unknown to our set of equations, and we wouldn't be able to solve the problem. But the key here is that we add one unknown to the unknowns, but we also get rid of one of the unknowns. If the disk is sliding, the value of friction force for the kinetic friction is known. It is F of F is equal to mu k times n. So this force, which was unknown, we were treating it as unknown, would become known when we have sliding. And that kind of like reduces one of the unknowns that we had, and we have one more unknown here. So this unknown kind of like replaces the other unknown, and still we will have the same number of unknowns as the same number of equations that we had. So this is the key for kind of like for problems that we have. I forgot to mention this point. This is the key for the problems that we have. We have rolling, and we want to see if we have pure rolling or no, we have a sliding also. So that's the key. Calculate the friction force, see if it is larger than the maximum stationary friction that we can, static friction that we can have. And if that's not the case, then that's okay, we have pure rolling. But if it is larger, if the friction force is larger than this maximum value for the friction force, then we do have sliding here, and also the value of the friction force would be known, mu k times n. So that's the key for solving these kind of problems. So I guess we are done for this lecture, and I think I see you guys in the next lecture. I try to post the homework maybe tomorrow, again on the kinetics of rigid bodies. Take care.